Our presentation tonight is on nuclear waste. It's by Dr. Jim Conca, and he's worked on nuclear and energy issues for 40 years at NASA and Los Alamos National Laboratory. Dr. Conca has been an advisor to the DOE, EPA, state and federal regulatory agencies and industry, and he was a science contributor to Forbes on energy and nuclear issues. Welcome, Dr. Conca, and I'll let you talk about nuclear waste.
Good. I'm going to share my screen. So I'm going to kind of dive right into this. It's not the stuff that you learn in high school, so we really have to go over a few things. Nuclear waste. There are 4 categories of nuclear waste in the United States. It's a little different in Europe because they don't have much bomb waste, and we have more bomb waste than we have commercial waste. And they're very, very different. So the first category is spent nuclear fuel. These are rods, so they're made of uranium oxide, and they're a solid metal, a bundle of rods. There's nothing liquid in there. There's nothing that can, leak out like one hears about the Hanford tanks, but that's the second category, which is tank waste, high-level waste. Now, high-level waste, by definition, is bomb waste. There's no such thing as high-level commercial waste. No such thing. There's spent nuclear fuel, which is commercial, and then there's high-level waste, which is bomb waste. Now, there's another category of bomb waste called transuranic waste, true waste. It's kind of a weird thing. It's mainly plutonium and americium and uranium contaminated. So, and I'll talk about how we get those two. And then the fourth category is low-level waste, which is mainly dirt and a bunch of other junk that's thrown in there. Some medical waste, some other waste, but by volume, it's mainly dirt. And it's not very contaminated. It's not very hot at all. So you don't have to have deep geologic disposal. So the first 3, spent nuclear fuel from commercial reactors, high-level waste, and transuranic waste from bomb-making activities, they require by law deep geologic disposal. Uranium-235 splits easily, fission. So then we're talking about fission. It's splitting a large nucleus into 2 smaller pieces. 238 does not fission easily. Okay, now if you look at uranium or natural uranium, it's only 0.7% 235, not enough to maintain a controlled or uncontrolled chain reaction. You have to smelt this ore just like you smelt iron ore. You get something called yellow cake, with U3O8, but it's only 0.7% 235. You have to be about 4%, depending on the reactor design, to produce fuel to run a commercial reactor. And so it's still mainly 238. So only 4%, 235, just enough to keep the reaction going and to create heat, to turn steam, turn a turbine, and create electricity. It's still mostly 238. That's very important. Nuclear weapons are all 239, and we'll get to that. So there's hardly any 238 left. It has to all fission at the same microsecond in order to get your blast. Now, why this works is that a neutron comes in, splits uranium-235 into 2 unequal pieces called fission products. 3 neutrons out and a bunch of energy. So 3 for 1. So in a microsecond, you're a 10 to the 20 split, and everything goes off in a microsecond. That's a bomb. And if you have 10 to the 20 of these fissioning at the same microsecond, you're going to create a lot of pressure. And that's your blast. It has nothing to do with radioactivity. Radioactivity is not why a nuclear weapon works. A nuclear weapon works because of the blast. So if you think about what happened in Hiroshima and Nagasaki, 250,000 people died from the blast. Only 800 people died from the radiation. So that gives you a perspective. Even though everyone focuses on the radiation, nothing to do with radiation. It's simply a big, big bomb. Again, it's mainly 238 still. It's only a few percent, 235. So those neutrons coming off the splitting 235 generally do not see another 235. They see a 238, which doesn't split. It captures that neutron, becomes uranium-239, and then quickly double beta decays into plutonium-239. We call this breeding. You're breeding plutonium-239 from uranium-238. All right? You're not fissioning it. You're not doing anything else. You're breeding another element from the original one. Now, the reason this is important is because 239 plutonium splits even easier than 235 uranium. So after 2 years in a commercial reactor, you're actually producing more power from the bred plutonium-239 than you are from the original 235 uranium. After 6 years, all these fission products build up to the point they start scarfing up all the neutrons and the thing fizzles out. It's not spent, it's not used up, it's simply too much junk in it. You've only used about 5% of the energy in the original fuel. Now you can take it out, you can recycle it. France does that, a few other countries do that. We don't, so we just set it aside, let it cool off, and we're supposed to dispose of it. Although you can burn it in fast reactors like Bill Gates is designing over in Bellevue. But anyway, this is commercial fuel. So after 6 years, you're basically got too much junk in there, so you take it out, you put it in a pool of water, you wait 5 years till almost everything is decayed away. Okay, all the really hot stuff is gone in 5 years in a pool of water. Then you take it out, put it in dry cask storage, and then the only two that are really left of concern are strontium-90 and cesium-137. But we will get to that. Now, if you're a weapons reactor, you want to make a weapon. Now, the thing that we wanted to do and that Russia does and that North Korea is doing is you want plutonium rather than uranium-235 because it splits easier. And therefore, you don't need as much, and it's lighter by mass. You can put it on a missile easier. So if you want to missileize your weapon, you want plutonium. So what you do in a weapons reactor, not a commercial reactor, weapons reactor, is you have to take this out after 6 months. And so what happens after 6 months is you start breeding in neutron poisons, things that scarf up the neutrons, and like plutonium-240 and plutonium-242. You can't separate those out. So you have to stop the reactor, take the fuel out after only 6 months. That's what we did out here at Hanford. And then you separate the plutonium and uranium, and you polish it, and you make your bomb, and you get all the other junk that comes out of it into the tanks. That's what's sitting in the Hanford tanks. So again, you cannot make a weapon from commercial spent fuel because it has too many neutron poisons bred into it over 6 years. So again, we know who's making weapons and who's not because we can see from satellite images who is taking out their fuel in only 6 months instead of 6 years. I should also mention now you have two types of waste. You have the fission products, which are the hot stuff. The fission products, the only thing that's really hot in nuclear waste. And the half-life for strontium and cesium is only 30 years. So rule of thumb is 7.5 years to background. So in 210 years, the fuel is not very hot. You can hold them in your hand. It wouldn't hurt you at all. I've done it. So it's not dangerous in that regard. You have to powder it and then breathe it in order for it to have any real danger. So the Hanford tanks, we won't really talk about those right now, but that's what these are. It's from separating the plutonium to make your bomb from a weapons reactor, not a commercial reactor. So if you have a weapons reactor like we had out at Hanford, we had 9 of them. And you can't leave it in more than 6 months. So you take those assemblies out of the reactor, you take off the cladding, which is the coating, and you dissolve it up in acid. And then you start separating, a series of separations. So you separate out the real junk that you don't want in your bomb because it will not work. So you separate those out, and those go into the high-level waste tanks. Then, when that's done, the remaining material is put through a series of polishing steps. And that goes into what we call the true waste. That's that third category, transuranic waste. And so these are generally the ones leaking at Hanford are the transuranic waste, not the high-level waste. Now, a weird thing has happened in the last 50 years. Since 1970, most of the cesium strontium has been removed, and the others mostly through 1 or 2 decay lives. So now the tanks do not have high-level waste in them. They only have transuranic and low-level waste. There is no high-level waste left at Hanford. Let me say that again. There is no high-level waste left at Hanford. Nothing in these tanks exceeds 1 curie per liter. So we'll talk about that if we have time at the end, but that's incredibly important. So everyone that talks about high-level waste at Hanford, there's not high-level waste at Hanford. Now, there's about, out of 57 million gallons, you could maybe call 600,000 gallons high-level waste if you really need to. Okay, if you really need some high-level waste to vitrify and call it a win, we can scare up 600,000 gallons. But the 57 million gallons are no longer high-level waste. Now, let's go back almost to the day I was born, 1957. National Academy of Sciences did a very nice study about what to do with nuclear waste. Now, the Atomic Energy Commission, the predecessor to DOE and NRC, we started making bombs, of course, in 43. And then we started the first commercial nuclear plant in 1957 on a shipping port. So AEC goes to the National Academy of Science and says, hey, listen, we're going to start making a bunch of this weird waste. What do we do with it? And they did a very nice study. I swear it was a half hour around the coffee table, because any geologist worth their weight in salt, pun intended, knows that massive salt is the only rock type you should put this stuff in. It will isolate it for 1 billion years. It takes 1 billion years for water to move an inch in this rock. And the best rock is in southeastern New Mexico, West Texas. We know this. We have a deep geologic nuclear repository working there, which I will talk about, that few people know about. And the reason this is so good, besides being massive and impermeable, it cannot maintain an opening, a fracture, a pore space, a room, it doesn't matter. As soon as you put this stuff in, as soon as you cut out a room, in fact, the walls, floor, ceiling, everything starts creeping in because of the overburden. If you're half a mile below the earth, the overburden will actually start to close everything up, because the salt is semi-plastic under a great pressure, okay? Not at the surface, but under a great pressure. It's nature's trash compactor. It's kind of funny, but it's what it is. And it's very, very effective. So that was 1957. So it shows the salt is best. Then the AEC establishes these new categories for waste. And then, okay, we're going to do deep geologic disposal for them, and low-level waste put someplace else. Then the EPA was formed. We decided not to reprocess commercial fuel because of proliferation concerns, which were not viable. There's no concern. You cannot make nuclear bombs out of nuclear waste from a commercial reactor. Like I mentioned, you breathe in too many poisons. So then we decided, okay, we're not going to reprocess. And then we might change our minds after we dispose of the spent nuclear fuel. We might want to get it back out. I mean, that's insane, but hey, you know, the greatest scientist in Congress came up with that one. So the idea that you would not want to throw away something forever and ever, you're going to spend billions of dollars putting it a half mile below the earth in the perfectly tight material, but then you might want to get it out. So we decided, well, you don't get it out of the salt because the salt closes relatively quickly. So you don't want to keep it open. So, okay, so everyone said, let's go find another rock, which was a dumb idea. It was a really terrible idea because this is the best rock. Now, unknown to most, transuranic, this category here, continue to go under the salt because no one even knows what transuranic is. So never discussed. So it kind of went under the radar and it kept going. And we have a wonderful repository for transuranic waste that was built and designed for everything. And it's been operating for 22 years brilliantly. Now, then the Nuclear Waste Policy Act came into existence in 1982, and that kind of ruined everything. Now, and as I mentioned, all the high-level waste at Hanford is only transuranic and low-level now. So there's not much high-level waste left. The biggest source, or the biggest stockpile of high-level waste was at Hanford, always has been. So 1982 comes around. The Nuclear Waste Policy Act called for 2 high-level waste sites. 2, not just one. There were 17 candidate sites, and the first was going to be in the west or the south, and the second was going to be in the north or the east. And then in a few years after that, the idea of retrieving spent nuclear fuel took hold, killing salts as the host rock, and by 1987, there were 3 candidate sites narrowed from the 17. You might recognize these. One was Yucca Mountain, Nevada. Another one was Hanford, Washington, right here, and then Deaf Smith County, Texas. Now, usually if I was in the room with everyone, I'd say, who was Speaker of the House in 1987? Well, it was Jim Wright from Texas. Who was House Majority Leader? It was Tom Foley from Washington State. There was this new junior named Harry Reid, and they said, Harry, it's yours. He was from Nevada. So from that point, you couldn't get elected dog catcher in Vegas if you were for Yucca Mountain, because it was seen as being shoved down their throats, which it was. It was a purely political decision. As we'll talk about, Yucca Mountain is a lousy place to put anything, and it's a terrible rock. I mean, you could do it if you spend enough money, but then you could make my backyard work. So Reid, of course, became Senate Majority Leader in 2006, 2008. Yucca Mountain license application was submitted to NRC. I was one of the original authors, very proud of the work we did. Very, very proud. Great work, even though it was a lousy rock, but that's okay. 2009, Obama killed it because basically Reid said he'd want my help in the Senate. You got to kill Yucca Mountain. I was very glad they killed it because it's a lousy rock, but the reason was very political, just like it was born politically. So people were saying, oh my God, politics killed Yucca Mountain. No, politics bore Yucca Mountain. It started it and then it was killed by it. So it's the same old thing. The original scientific decision was salt, and that still is the best decision. So in 2009, President Obama put together a Blue Ribbon Commission, and it was a brilliant commission. I loved it, worked with them, hosted them down at WIPP, down in the salt, where we have the repository that I'll talk about, to develop a new strategy. And of course, everyone ignored it. So this is Yucca Mountain. Now I want to mention Yucca Mountain, the Topopor Spring tuff, which is a volcanic tuff, is a highly fractured, oxidizing, variably saturated, dual porosity hydrologic system that sits on the edge of the Las Vegas shear zone. Now, which of those terms makes you feel good? None of them. They're terrible. So as a result of that, we had to institute extreme re-engineering at great cost, an extra $200 billion, but we're rich, in order to counteract the fact that we chose the wrong rock. So we had to come up with 7 engineered barriers to make this even possibly work. And I'm an engineer barrier guy, so great work, wonderful, but unnecessary if you choose the right rock. So if you choose the wrong rock, it's very difficult, very time consuming, very expensive. If you choose the right rock, it's easy, it's cheap, quick. So there is the right rock, and that, of course, unknown to most people, is in the salts in southeastern New Mexico. The repository is called WIPP, the Waste Isolation Pilot Plant. It's been operating for 22 years. All right, here's the surface facility. Here are the trucks that bring in different types of waste. This is the 72B cast. This is just what you would do for commercial spent fuel. This is how you transport it on the roads. We do it all the time. It was designed and built for everything, but it was only permitted for transuranic waste. We know how to handle this waste. We've been disposing of it for 22 years. It's a piece of cake. It is a piece of cake. I'm not kidding. Worked there for 10 years. Brilliant. It was very nice to work on a project that actually was working. Now, 16 square miles was set aside in 1992, the Land Withdrawal Act. When WIPP is full, only a half to 1 square mile will be used. There's plenty of room in the 16 square miles for all the nuclear waste we could possibly produce in 500 years. Now, what's interesting is that WIPP is ahead of schedule and under budget. Now, please tell me what federal program is ahead of schedule and under budget? No one, because this is the right rock. Yucca Mountain is 30 years behind schedule and $200 billion over budget because it's the wrong rock. Now here's WIPP, the surface facilities. There are 4 shafts into the underground: air intake, air exhaust, salt handling, and waste handling. So these are panels that are cut into the rock a half mile below the earth. Each panel has 7 rooms, and each room is a football field in length and can hold 12,055-gallon drum equivalents of waste, or whatever container will fit on the trucks and fit into this repository. Now, the reason this salt exists and why it's so good is there was a little Proto-Pacific arm that came into southeast New Mexico and West Texas from the Proto-Pacific Ocean during the Permian about 270 million years ago. For tectonic reasons, that arm kept getting shut off and evaporated, shut off, evaporated, flood, evaporate, flood, evaporate, flood, evaporate, over 30 million years. And it precipitated 6,000 feet of salt, the top 2,000 of which is particularly pure and perfect for this application. And if you look closely, hold it up to a light, it's got little tiny square bubbles, crystallographically trapped 270 million year old seawater. And we have looked at that, and there's DNA, 270 million year old DNA, the oldest DNA we've ever found. Organics don't last that long, is a testament to how isolated this rock is. There's no naturally occurring radioactive materials like uranium that's in the walls right beside you, or the floor, or the air, radon. There's nothing down there except salt, and this is sodium chloride. Salt. I actually used to chop off pieces and make margarita salt out of it. It was very funny. Again, Nothing has happened in 270 million years to this rock, and nothing's going to happen for the next 200 million. And it takes water 1 billion years to move an inch in it. So there's nothing like this. We couldn't have manufactured a better rock. Now, in 2007, we actually started shipping the high activity waste, the hot stuff, to WIPP. Never had a problem. It's a piece of cake. For the hot stuff, we robotically drill a hole in the wall. So this is one of those rooms in the panel I mentioned. It's pure salt, pure sodium chloride, and you robotically drill out a 15-foot hole, and you robotically push in your hot waste package and then seal it with a 4-foot metal wrap cement plug. So if you look at the walls, here is the hot stuff in the walls with a 4-foot metal wrap cement plug. So here is one of the waste rooms that's being filled. If you have a chance to go down there, it's actually brilliant. I used to lead trips when I was down there, congressmen and other people, and everyone loves it because it's so easy, it's so simple, and it's working. So here's this person. This is a half mile below the earth. This is a pure salt, so there's no natural occurring radioactive materials like uranium in every soil. Cesium is on the surface. We're bathed in radiation, about 600 millirem a year. Right now, this person was getting 1/10 of the background radiation that you're getting sitting there watching this because he's a half mile below the earth. And this is nuclear waste, the plutonium and uranium and americium stuff that's only alpha, some beta, and it can't get through 1/4-inch mild steel, so it's easily shielded. And the really hot stuff is in the wall, robotically put there and plugged. So this guy, the only real dose he's getting is from the potato chips he ate that lunch. And as you know, potato chips are the most radioactive food, right? You know that, right? It's no big deal, but it's kind of funny. So after 23 years of operation for this deep geologic repository that can handle everything, was designed and built for everything, and there's tons of room, over 150,000 cubic meters of transuranic waste, more than all of the commercial waste combined, has been disposed of, the equivalent of 700,000 55-gallon drums. 22 storage sites, including Rocky Flats, is in WIPP. There was one minor release. It didn't do anything, didn't get anywhere, no one contaminated. That was in 2014. And it wasn't WIPP's fault. Someone from someplace else put the wrong stuff in the drum. It's okay. WIPP worked perfectly the way it was supposed to work, and no one was contaminated. Now, what happens when you put the waste in here? And EPA requires we have at least one engineered barrier, so we chose magnesium oxide salt. It's great, it absorbs plutonium, absorbs water, absorbs CO2. It's really neat, it's cheap. We don't need it, but okay, we had to have one. So when you fill these rooms, I mean, immediately the wall, floor, ceiling starts coming in. And so in 10 years, you start crushing this down. And in a couple of 100 years, you're back to where the rock was in the beginning. And so I hate to throw complicated science here, but this is hydraulic conductivity and this is diffusion coefficient. Those are very low numbers. Again, you couldn't manufacture a rock this good. The pH is ideal for holding radionuclides like plutonium immobile. You need to be acidic to really move the stuff. And the EH, or the reducing power, no free oxygen, that's free hydrogen, it's very reducing. And that makes things like technetium and plutonium and neptunium not move at all. Okay, so you want the EH to be really low, and this is the lowest EH water in the country, so it's ideal. The thermal conductivity of salt is 5 times that of granite or tuff, like at Yucca Mountain. This creep closure ability of the salt goes as at least the 6th power of the temperature, which means that it closes really quick the hotter you are. So the hotter the waste is, the better this rock works. And you can't even imagine a rock this good. So you just handed, with no effort, a performance period of 200 million years. And for Yucca Mountain, we had to work our butts off for 10,000 or 100,000 years, because with using all those engineered barriers and everything, because the water is dripping, it's oxidizing. It's just not a good place to put this waste. Whereas this salt, you don't have to do anything. Just get it there. You don't need to do anything except meet the Department of Transportation requirements to get it on the road and get it there. So here's the 16 square miles set aside for WIPP. The final footprint, when it's done with its present mission, will be about a square mile out of 16. WIP is, again, 10 years ahead of schedule and $1 billion under budget. Now, if you increase, put the Hanford tanks there and all the bomb waste from Savannah River and everything else, you might double it to 2 square miles. So again, this can handle all the waste we could possibly generate because we're not generating any more bomb waste. And bomb waste is the most voluminous nuclear waste there is. Commercial waste is not even a third of it. Okay, let's get to the Hanford tanks now. These, again, are weird. It was formed by that process chart I showed. I want to throw this out because it's very, very important. Hanford tank waste poses no measurable risk to human health and the environment off-site. Off-site. There is no mechanism, geologic or otherwise, atmospheric, hydrologic, there's no way to get any of this waste off-site to any appreciable degree that it's going to hurt anyone, not even Richland, which is right next door. Okay, and we'll talk about that. Now, that said, it poses only a small risk to workers on site. So the people that are handling it, they're the ones that are taking the risk. The public has no risk to this. And the risk is greater if you vitrify the waste. Leads you to wonder why we're vitrifying the waste. We're vitrifying it because it was supposed to go to Yucca Mountain. Yucca Mountain will never open, but it was vitrified to go to Yucca Mountain, where the waste form mattered. So again, back to this graph here, this cartoon. So the waste tanks filled with this mucky peanut butter-like junk with salt cake on it. I mean, it's really nasty stuff. And so you can't transport that as is, because Department of Transportation requires no free liquid. It has to be solid with no free liquid, because the more liquid you have in it, the more possibility of actually something can leak. So it has to be solid. So again, the high-level waste tanks, which are no longer high-level waste, were the first 2 processing steps, and then the polishing steps went into the true tanks. And again, as I mentioned, most of the hot stuff is gone, so it's all true or low-level waste. Now, Hanford site's kind of bizarre. It's a very complex subsurface stratigraphy, layers that are all weird, and this came from the Bretz floods during the last glacial era. So it's kind of mixed up. It's kind of weird. Some things are tight. Some things are very not tight. So where these tanks are, it has to come down, hit the water table, and then move towards the river. So all groundwater flow in this region is towards the Columbia River. Okay, it can't go in the other direction. It's all towards the Columbia River. So that's really where you're looking for your modeling to tell you what's going to come out on the banks of the Columbia River and when. So the time frame that we use, 40 CFR 191, is that within 1,000 years, there can't be more than 4 millirem per year whole body. 4 millirem is really tiny. Regulatorily, it cannot exceed 4 millirem at the river's edge. Well, in the first 1,000 years. 10,000 year requirement is 1 in 10 chance of exceeding 4 millirem per year. Now, we really concentrate on water because that's the pathway that is most likely to get out. We aren't going to be eating it. We're not going to be doing anything else, but it could contaminate water. So if you're looking at some futuristic family farm in the year 5000 or something like that, then you want to know what's going to happen to the groundwater that's going to be intercepted down gradient from this site, or will it get all the way to the water's edge? This is the kind of modeling you have to do, and you have to go back to all of these units and collect all of the samples in order to get the characteristics of each unit in order to plug into your advection, diffusion, dispersion equations for how radionuclides are moving through the subsurface, the same time how they're decaying. So it's kind of complicated. It's been 10 years directly measuring properties in these rocks to plug into this. Several other people were doing the same thing. We actually know this very well. Okay, we know this much better than climate change modeling, which we are getting to know very well too. So again, our modeling capability is quite good. The one thing the Yucca Mountain Project did was perfect our modeling. I mean, a lot of that money that was spent in Yucca Mountain wasn't wasted at all. It was, went into computer modeling, it went into transportation studies, corrosion studies, all information that can be used no matter where we put this. So don't think of Yucca Mountain as being a waste of $12 billion. It wasn't. It was maybe wasted $1 billion over 30 years. I mean, that's not even one bomber. So at the river's edge, the regulatory limit off the 300 area is 4 millirem per year at the river's edge. Now, once it comes out at the river's edge, it enters the Columbia River and it's gone. You can't even measure it because it's so diluted. But at the river's edge is where it cannot exceed 4 millirem per year. So we do the environmental impact statements, we do all that modeling, and we come up with scenarios. Okay, now the number one scenario is no action. You just walk away from these tanks. You don't do anything. You just walk away from them. Maybe you fill them in with sand or put a record cap on it or something, but you don't treat them. You just walk away from these tanks. Let them leak into the ground and everything else. All these other alternatives are different types of vitrifications. This column is the radiation dose per year, millirem per year. Remember, background is 600. The hazard index is no big deal. It's, closer to 1, it's great. And in the parentheses is the year. So in the year 4978, which is amusing because we don't, the confidence in these numbers is one significant figure. So about 5,000. In the year about 5,000, the peak dose, if you do nothing, you walk away from these tanks, is 4.37 millirem per year, which is also funny. That's 4. For all these others are different versions of vitrification. So you would then drop from 4 to 1, because 0.9 is 1. All you're doing is dropping from 4 to 1. You can't clean up this bit because that's already leaked out. So what has already leaked out then dominates. All right, you got that? So what has already leaked out is leading to this 1 millirem a year. What's left could triple that. But tripling from 1 to 4 when the background is 600 is kind of bizarre. Again, the latest update was 2013. It was updated from 1980. And the background has gone up significantly, mainly because of medical procedures. We do a lot of medical procedures, and if you pass someone who's had a medical procedure on the sidewalk, you will get a little dose, but again, not very much. So this is the background, and it's mainly from natural materials and then medical procedures. Everything else is almost nothing. So if you look at the worst case, you just walk away from these tanks at the river's edge in the year 5,000, you're going to get an additional 4 millirem. It's like taking a flight from Seattle to New York and back. That gets you 4 millirem. Of course, worse, of course, if you move to Spokane, you're going to get 50 millirem. Now, should we outlaw that? Well, maybe. But no, this is absurd. And this is the worst case. It's the worst case. So if you actually vitrify it, it's going to cost you an extra $200 billion, but okay, you open Yucca Mountain, it's going to cost you another $200 billion. Then you can drop it from 4 millirem to 1 for spending $400 billion. Now, although DOE wasn't allowed to make this estimate, a lot of us have done enough work with grout, we can make this estimate. And so if you just grout the tanks, whether you grout them and send them to WIPP or you grout them in place, doesn't matter, you're removing the source term. And so that drops it from 4 to 9.9. So it's the same as vitrifying, except it's almost 10 times cheaper. But that's okay. If you want to do that, great. State doesn't like that idea, doesn't like grout. But the funny thing is that we've worked on grout. I came up with at least 2 formulations that work better than glass. Less leachability, greater compressive strength. So it's like grout's great because this waste in the Hanford tanks chemically does not like to be in glass. That's why we're having so much problems doing this. It does not like to be in glass. It likes to be in grout. So we had a grout program in the 80s that was brilliant. Should have continued, but then no, we're going to do glass. Okay. So glass, it's going to cost about $160 billion over 60 years. It triples the volume of the waste. We generate a lot of secondary waste during the vitrification process. Most of this is low-level waste. So vitrifying low-level waste is insane. I mean, no one ever does that. An additional 40,000 gallons of diesel per day, it'll double the carbon footprint of Hanford. If one cares about that, you might not. Now, grout, waste chemistry, very compatible with this grout. No technical hurdles. We've been doing this. We know how to do it. It's a well-known process. It only costs $50 billion over 30 years. Modest increase of volume of waste, but not tripling it like that. Like grouting is a standard method for transuranic waste. So this is a standard method. We already know how to do this. No additional fuel needed, little effect on Hanford's carbon footprint. So, I mean, if you were to just, as a scientist, just choose which one of these you would do, of course you'd choose grout. But scientists did not make this decision. Now, for commercial spent fuel, interim storage is great. It's good for about 120 years. And if you need to move it to another die-cast storage, that's easy to do. So, hopefully we're going to burn this fuel in fast reactors like Bill Gates is designing. Brilliant. You get 10 times the amount of energy for the same amount of waste. That's what you want to do. And then that waste is very short-lived. It's all fission products. And then you can put that wherever you want to put that. Now, you probably heard about borehole disposal lately. It's kind of become a big thing. And we can drill boreholes to 5 kilometers. That's not really a difficult thing. The only difficult thing is how wide do you want your drill hole, your drill bit. So if you're grouting something, you can make it as thin as you want, and you can make it thin and long, and you can put it down a borehole really well. If you get down to 4 or 5 kilometers, there is no geologic process that can get it back up. None. So this is easy. It's simple. That kind of scares people because they were told it would go someplace else. But this is a very nice thing to do, especially when you burn the present commercial fuel in fast reactors, again, like Bill Gates is doing. Then you can make the size of your disposal to go down the borehole as thin as you want. And it's easy if you use a thin borehole than if you use a very wide borehole. So we can do this. Again, we do it all the time in fracking. We know how to drill holes. We know how to drill holes sideways, diagonal. We can do this very easily. So what we're left with is this. This is the probable outcomes for the United States nuclear waste. This is it. There's no other alternatives. I hate to say this, but this is it. So defense waste, which is all true in high-level waste, if you redefine it as true, like it is, or as low-level waste like it is, you can put that to WIPP. Of course, that's a political decision, because then you'd have to expand WIPP's permit, and the state would have to buy into that, and all this, political nonsense, because everyone's so scared of it, not knowing why. High-level waste we define as low-level waste, which is most of this 57 million gallons. We actually have a place for that. It's in Texas. It's called Waste Control Specialists. They do this all the time. They accept low-level waste and bury it there. Or we could build a second salt repository like WIPP, but that's kind of foolish. We already have one. Only need one. So either we do that, or everything stays right where it is. But if I had to put money on it, everything's going to stay right where it is, because we can't seem to make a national decision anymore as a country. We're like 50 children arguing. So we can't make a national decision, and nuclear is a national thing. Okay, there's no constituency for nuclear like there's, Texas for oil, or Pennsylvania for coal, or for natural gas, or West Virginia for coal. There's no state that identifies with nuclear. Burn it in fast reactors like Gates is building, and then that waste, which is only fission products now, all short-lived, then that could go into either, just wait till it cools down. It's cool in 200 years. Again, into WIPP. If WIPP were expanded like it originally was decided by the National Academy of Sciences, this is where everything should go. All nuclear waste should go into this salt. But again, if we can't come up with that, then it's going to stay right where it is. Thank you. Questions?
What's the millirem per year limit for fish and other aquatic organisms?
It's the same. There are food limits. Let's see, in the US, it's on the order of 7,000 becquerels per kilogram of fish flesh. I would have to convert that. But the dominant one is this 4 millirem per year in terms of water. Okay, and water is very, very important, because that's where things live and that's what we drink and all that kind of thing. So it never gets high in fish or anything like that, unless you have something that concentrates up the food chain like lead or mercury. But we don't see that with radioactive material.
The Bill Gates reactor, I think that's the traveling wave.
Okay, no, actually they've dropped the traveling wave. They have a molten salt fast reactor. No, this is not a conventional reactor going into Wyoming. This is a molten salt fast reactor that can burn traditional waste. All right.
Yeah,
yes. Now I should back up a little bit. We have built that reactor. We had FFTF up here out of Hanford in the 80s and 90s. We built a fast reactor. In fact, all of the new designs that are coming up, pebble bed reactors, molten salt reactors, fast reactors, we've built them all as experimental reactors, and they worked. We know they work. We just have never commercialized it. So when you commercialize it, that's a big step because someone has to make money, right? It has to be commercially viable. And so that's all that everyone's trying to do is build a reactor that is commercially viable. We know it works.
And if you mind, when I spoke with Mark Werner over there at TerraPower, they indicated that the first few iterations of fuel would be conventional HALEU fuel, not waste burning, but that is where they're headed. So it is like multiple iterations, and we will get there someday.
As I mentioned before, most reactors take 4 or 5% 235, but in HALEU reactors take up to 20% uranium-235. That gives you much higher power, much higher neutron flux, and that's what it takes to initiate fast reactors, because you need a lot of neutrons that then just blow out everything, burns americium, burns neptunium, burns everything.
How soon, I guess, do you think that we'll be able to burn waste?
Well, Gates's TerraPower is looking at 2035. Is that right, Carl? About 2035?
I believe it needs to be done by 2029 is the timeline for things to get either really interesting or slightly disappointing.
Right.
So by 2030, we should have proof of concept power being produced with waste fuel.
It's also done in other parts of the world, isn't it?
China just fired up their first commercial fast reactor. So they're doing it. Okay, so again, the concept is already old and done. All that we need to do is commercialize it. Because a lot of times, going from the laboratory or from experimental stuff to the commercialization, there's a hurdle there to make it cost effective. Now, China's already made it cost effective because they can build their reactors half the price and half the time that we build it, because they don't use subcontractors, and everyone that walks off the job, they get to get new people, they have to retrain them. I mean, the way we do things in this country is not advantageous towards moving forward on climate change like we need to do. We tend to, run around and dance around and do stupid things instead of what we need to do.
Yeah, I thought INEL had a fast reactor that actually powered Arco, the city, for the first time in the 50s.
Yes. So again, most of these designs come from the 50s. In fact, Edward Teller came up with the traveling wave reactor. 50s and 60s, we actually did a bunch of things. They didn't get commercialized. We chose the light water reactor, but what we have now is incredibly safe and effective. I mean, no one ever dies in the nuclear industry, as opposed to every other industry. Everyone says, as long as it's safer. It's like, how safe is 0 deaths? I mean, how much more safe can you be not killing anyone? So it's kind of bizarre. Now, I should mention that there's been no reactor that the Nuclear Regulatory Commission has approved that has ever melted down. 3 Mile Island was before the Nuclear Regulatory Commission came into being.
It didn't melt down, actually.
Yeah, I mean, it's a partial meltdown. It was no big deal. The only accident we've had was in a pre-NRC world. And of course, Chernobyl, Fukushima, we told them those are stupid reactors and they shouldn't do them. But hey, the Fukushima thing, we've been telling them for years that their seawall was crap and their backup generation was crap. But, hubris and greed, bad combo in anything. Yeah. But still, no one died from radiation at Fukushima.
It's kind of on that same line. Are the reactors that have been in use by the Navy for, 50 years, are they a different kind of technology than our typical large pressure water reactors?
The higher amount of uranium-235, the less you have to refuel. So if you want a nuclear sub to go for years and years without ever refueling, then you use more highly enriched uranium. But it's the same reactor design. It's a small modular reactor. In fact, they're the first small modular reactors, but they're traditional pressurized water reactors.
Yeah, pressurized water reactor, 98% enriched, and very effective. Just like in the salt mines, when we were down on the sub, we got less radiation than people walking around on the surface.
Right.
Never had an accident, very safe, never had a spill, never had anything like a meltdown. We know how to do it.
I want to go back to a general question that Catherine asked. And she said, I'm just curious, in terms of nuclear power policy right now, which country on the planet is the most enlightened? I've heard France has done the best so far.
France has done great, but China is the one leading the way. China is breaking ground on a new nuclear reactor every month, and they are building it. To have 180 big nukes, not small modular, although they're building small modulars too, but 180 big nukes by 2035. That will dwarf us, and they need it. Now they're also building coal, and they're also building gas, they're also building hydro, because they need to bring an additional 600 million people up out of abject poverty into the middle class, and they don't care how to do it. They're just building everything. They're building more renewables than everyone in the world. They're building more nuclear than everyone in the world, more coal than everyone in the world, because they need energy. There's always been this dynamic tension between humans and the environment. Now, when there was only 10 million humans on the planet, which was the last 200,000 years before about BC, that wasn't a big deal. Okay, but then the Industrial Revolution came along, and here we're now at 8 billion, almost 8 billion people, and you need to power them because it takes about 3,000 kilowatt hours per year per person to have what we consider a good life. So the only way to say, no, keep people in poverty, we care about global warming, not going to work. And it's also kind of nasty because when you get 3,000 kilowatt hours per person per year, the birth rate plummets. It's a very nice side effect because when you have enough energy, you begin to feel that you will live to age 40 and that your children will live to age 40. And that opens up a huge philosophical change in the society in which it's occurring. And we've seen that in every single society that has become, quote, developed. And that just means you have a lot of energy.
Excellent. Michael Ruby asked if burning waste fuel would change the economics, since you'd be paid to take the fuel instead of paying for storing it.
Yes, and of course, if you get 10 times the amount of energy out of the same fuel, right there, your economics are wonderful.
Do we know who in Congress or elsewhere in government is supportive of using nuclear for energy generating purposes?
Good question. Congress, there's a handful of congressmen that like it, but generally, if you're Democratic, the base doesn't like it for ideological reasons, although they don't actually understand it, but they just don't like it, okay? They've been told not to like it. Republicans care about fossil fuels.
We're working on that.
Yeah, and we're working on that. But the southern states are more pro-nuclear, just like us. They are regulated. They're in regulated electricity markets. Unregulated electricity markets are bad. Okay, I'll just state that right out. Bad. The cost of electricity is double or more, and they tend to not like nuclear because they can't manipulate the power that comes out of a nuclear power plant because it just produces power all the time. 95% of the time, nuclear is producing power. So you can't mess with it easily. So if you're peaking, if you're saying, oh, okay, you're going to charge twice as much for a kilowatt of electricity between the hours of 3 and 7 at p.m., and so, okay, we're just going to charge you this, and we're going to fire up a bunch of gas plants, or we're going to shut down a bunch of wind turbines. So an unregulated market is adept at ripping us off. Sorry, that's about the best way to say it. Regulated markets like we have, you can't. So the nuclear power plant out here, Columbia Generating Station right next to me, they're not for profit. And they are only allowed to sell electricity at cost. They can't gouge you. Now, in Texas during the blackout last year, ERCOT, the transmission operator down there, they gouged everyone. I mean, they charged people because they caused the blackout, okay? But they charged people, the consumer, $1,000 extra for that summer. Now, that is wrong. I'm sorry. We've been telling ERCOT, that you're stupid and what are you doing? Because they purposely didn't hook up to the rest of the country so they could get around FERC regulations, Federal Energy Regulatory Commission. So they didn't hook up to the rest of the country. They stayed within the state of Texas, so they didn't have to follow regulations. Now that is supremely greedy and kind of dumb because when you don't follow regulations, bad things happen. I'm a regulatory hound. I love regulations. They're great, okay? That's how you wrangle corporations. It's not a corporation's job to save the world. Corporation's job is to make money. Okay, I get that. It's America. Something got to make a buck. I get it. But regulations are what keep that to a minimum sometimes if you follow the regs. But if you get around the regs by some cute thing like Texas has done, then all bets are off and the consumers The people of Texas are going to suffer because of that.
So a follow on also, Jim, thank you for that. Is how long do you believe it's going to take? This is again from Jim Bloss, to change the public's belief and support of nuclear power.
I hate to say this. I really hate to say this. It's being recorded, so I can't take it back. Enough people have to die. I really hate to say that, but that's how humans work. Enough people have to die or go bankrupt or have, rolling blackouts where during a heat wave, and people die during heat waves when there's rolling blackouts. I mean, Texas, there was a coal spell and about 170 people died from that blackout, and it caused $3 billion in damage. So we have to have that happen a few times before people say, hey, wait a second, you're supposed to be running this. You're supposed to be giving us reliable power. What's going on? Can't do coal, can't do gas. What are we doing? All right, well, you should be doing nuclear and wind and solar and hydro, all the non-fossil fuels. But what we're doing is wind, which has no backup. So it doesn't deliver when it's really hot or really cold. So we are headed for some very bad blackouts post 2025. That just, all the public utility district commissioners are scared. I'm not just worried. They are scared because there is no plan in place to replace coal with anything except wind, and wind doesn't do it. I mean, you need a reliable source. If you want a Green New Deal that works, you got to use all of them. Okay, we don't have the luxury to pick and choose. We don't like wind or we don't like nuclear or whatever. You don't have that luxury. Okay, you're trying to replace fossil fuel, which is 80% of our energy in this country, 80%. And you're going to cut out something like nuclear or wind? I mean, come on, that's insane. So you got to do everything as fast as you can. And we're just pokey. I mean, it's just because not enough people have died.
I think just to also bring this home to Washington State, a lot of people believe that we have enough hydro and that we'll manage and that there won't be brownouts or blackouts. But the water situation is not as straightforward as one would think. And maybe you'd like to comment on that.
Yeah, so if you look at the day-by-day load graphs out of Bonneville Power Administration, it shows you what's coming on the grid, what's going off the grid, all that kind of thing. Nuclear just is constant. Coal and gas just constant. Whenever wind comes up, hydro goes down. And so hydro is used to balance the grid, all right? And that's great. We have a lot of hydro. That's wonderful. But we don't have enough if you get rid of all the thermal sources. We don't have enough. And again, climate change is going to affect things. The Columbia River is not much affected by climate change. That is fortunate for us. It's not much affected because its headwaters are way up in Canada, and there's lots of snowpack, and there will be lots of snowpack even with extreme climate change. But the Yakima River is going to die, and the Snake River is going to go down quite a bit. But still, we don't have enough power if we get rid of everything else. Especially since we're talking about decommissioning the Snake River dams, which is amusing.
So thank you very much.